Hey there, welcome back to this video, lesson 2 in Unit 1B. We're talking rational functions and specifically how do you identify the discontinuities of rational functions wholes, and then we'll introduce how we identify vertical asymptotes as well. Okay, we're going to go ahead and jump back in, and we're at this example here that says the rational function n is defined as n of x, which is equal to x cubed over 4 minus x over x squared plus 3x plus 2. In the xy plane, the graph of n has a hole at the point with coordinates c, comma, l. Find the values of c and l. So don't get confused by the c and l. They just want to know, they say, hey, there's a hole. What's the coordinate, okay? And so what we're going to go ahead and do, again, what you need to do with these functions is you need to factor. So I'm going to take out a factor of x in the numerator, and in the denominator we have x plus 2, x plus 1, and we can go further with our factorization in the numerator, and we get x times x minus 2 times x plus 2 all over x plus 2 and x plus 1. Okay, so what you should notice about this, again, a whole is a shared factor. So it looks like I have an x plus 2 that is shared. So this is going to be the location of our whole, okay? And so we are going to go ahead and say, okay, I have a whole at x equals negative 2, right? I take my x plus 2 factor, I set it equal to 0, and I solve, we get negative 2. Okay, so that is what they call essentially c here. So c is equal to negative 2. That's my x value. And what I need is I need the y coordinate. So my reduced function or expression is going to come in handy here. So this is my new function without the discontinuity value. If you plug in negative 2 into your original function, you're going to get an indeterminate. You'll get 0 over 0. I don't know what that is. So we're going to go ahead and plug in now negative 2 into my reduced function. So this function was called n. So n of negative 2 is equal to negative 2 times negative 2 minus 2 over negative 2 plus 1. And so it looks like, what do we get? Negative 2 times negative 4 would be 8 over negative 1. And so we get negative 8. Okay, so L is equal to negative 8. There you go. There's C and L. Okay, let's go ahead and look at the next example. This example says a rational function f is given by f of x equals x minus 1 times x plus 7 over x minus 1 times x minus 5. In the xy plane, the graph of a rational function f has a hole at x equals 1. And we can go ahead and we can see that. Right? We can see that here because we have a shared factor at x minus 1, and those will end up reducing. They say, which of the following is true about the graph of the function as x values of x become sufficiently close to 1. So here's what we're going to go ahead and do. They have limit statements here, and they want to know as x becomes sufficiently close to 1. This is this idea of a limit. As I get really, really close to a certain value, what is the y value approach? Well, since they want to know what, as the x value becomes sufficiently close to 1, check out these two. You see how they say as x approaches negative 2? Those are talking about x equals negative 2. So ignore those. They, those are not going to be answers. So, but what we can do now is we have a y value of 0, and we have a y value of negative 2. So what is the location of the whole? Essentially like the question above. So it does take knowing the reduced function, which we just calculated, x plus 7 over x minus 5. And what we're going to do is we're just going to plug in that 1 value, f of 1. What is f of 1? So we get 1 plus 7, which is 8. 1 minus 5, which is negative 4, and so we get negative 2. Answer B. Okay, so pretty easy there once you understand what's the question saying, right? Okay, here is a couple of practices very similar to what we just talked about. Go ahead, pause me, answer this one, and then I will go over the answer. All right, hopefully for this one, you canceled the x plus 6 factor, meaning you have a hole at negative 6, and then we evaluate our reduced function at the negative 6. So when you do that, you should get a negative 12 over a negative 3. Two negatives make a positive. Answer is a positive 4. B. Did you get it? Hopefully you did. Okay, another practice one. This is the last one idea about holes before we jump to asymptotes. Go ahead, pause the video. Try this one. Okay, for this one, the answer is C. Now, how do we get C? They say the function has a hole at 3. So right away, you should be looking for, hey, I need a factor of x minus 3 top and bottom. Now, D and A do not have that. A has an x plus 3. That would be a hole at negative 3. So good tricks there. So we're looking at B and C, and I highlighted that x minus 3 factor. Then they say input values of R sufficiently close to 3 correspond to output values arbitrarily close to 8. So essentially, if I have a hole at 3 and I reduce, if I plug in 3, what's the y value going to be, is what they're saying. And so if you, I guess you just kind of have to do some checking. I did check C first. I canceled those, and then I plugged in 3, which gave me 8 over 1. And C was the answer. For B, that's what it would look like. It looked like 8/5 on that one, okay? All right, now let's go ahead and let's talk about vertical asymptotes. Vertical asymptotes, if I go ahead and scroll back up here, vertical asymptotes look like this, and they come from discontinuities or values where a value of 0 is created only in the denominator. So if you have shared factors top and bottom, that's going to give you a hole as long as the numerator is equal to or greater than the factor in the denominator. If you have a factor even after all the reducing in the denominator, that is going to be a factor that creates a vertical asymptote. Okay, so as your values approach it, your function values go up towards positive or down towards negative infinity. Okay, so again, that's visually what they look like. Now let's go ahead and see kinda what this looks like here. Okay, so here is a rational function m, and we just want to find the x-coordinate of any vertical asymptotes. The first step you're going to do with vertical asymptotes, one is reduce. I need to go ahead and reduce, I guess factor and reduce. Maybe add this again, right? This whole idea of factoring in this unit is huge. So let's factor this. I have x minus 4, to the power of 3, x plus 1 over x times x minus 3 times x minus 4, x plus 1, it looks like. Okay, and so I'm going to go ahead and I'm going to, cancel some shared factors. So it looks like, okay, x plus 1, we got a whole, x minus 4, I only have 1 here though, so that's going to make this a 2, and that is it. So here's our reduced expression. So x minus 4 squared, x over x minus 3. So I want to be clear here, you would have a hole at x equals -1, and you're going to have a hole also at x minus 4, because I had a shared factors top and bottom, okay? Now, what's left over in my denominator? Well, right here, if I set my denominator equal to 0, x times x minus 3 equal to 0, we get 2 zeros. I get x is equal to 0, or I get x minus 3 is equal to 0, which means I have a hole at x equals 3, right? I add 3 to both sides, plus 3, plus 3. Okay, so these are what we call vertical asymptotes. Okay, at these two locations, x equals 0, x equals 3. And I'll often abbreviate vertical asymptotes as VA, right? So there's your vertical asymptotes. Okay? All right, let's go ahead and let's look at this again. Here's example number 2. Ooh, nice, they factored it for us. That's cool. But we need to go ahead and we still need to reduce. So it looks like, okay, x minus 5. There's going to be some holes there. And then, ooh, look here. I got some x plus 6's. There's 2. That's going to cancel 2 of these, so I still have 1 in the denominator left, right? So what is our reduced function? Well, it looks like I don't have any factors in the numerator, just a 1. And then I have an x plus 6 to the power of 1 and an x plus 2. Now, I know that there were shared factors here, and we've been so used to, hey, if you have a shared factor, it's a whole. Well, not always. If you reduce and you still have this factor in the denominator, then that is a vertical asymptote. Again, all of these are going to give me vertical asymptotes. So x plus 6 equals 0, x plus 2 equals 0 means I have vertical asymptotes at -6 and -2. Okay, these are the vertical asymptotes. There you go. So if you reduce and you have a factor in the denominator, it's an asymptote. What if it was a whole? Well, it can't be a whole and an asymptote. And the asymptote is I guess, a bigger bully. Okay, so asymptotes win in this case, right? Because they're asymptotes. All right, let's go ahead. Here is a practice question. Let's see if you can kind of retain and demonstrate knowledge on this. Let me double check. There looks like a space there. I just want to make sure. Yeah, there's supposed to be a 14 right here. My notes left it out. Okay, so I'll make sure that that's clear. 14. All right, pause me. Can you identify the asymptotes? We'll see. Okay, here is your factored form. You just had to factor this trinomial, which is x minus 7, x plus 2, once you know that that's a 4. And it looks like we have an x minus 7 that cancels and reduces. And then we also have some x's here that cancel, and then x plus 2 that cancels. So again, because the numerator is bigger here, that x equals -2 is going to be a whole, right? Because I shared factor, that's a whole. The x minus 7, the denominator is bigger, so that's going to be an asymptote. So that's one of your vertical asymptotes at x equals +7. And then again, I had this shared factor of x, which gives you a vertical asymptote at 0, since the degree is bigger in the denominator, okay? Just a couple of notes here. If you ever see this notation red, k, red of x, it probably means reduced. This is the reduced function of k after we took out any duplicate factors in the numerator and denominator. Okay, so vertical asymptotes 0 and 7. Did you get it? Did you get it? Okay, if not, here is your second chance. Go ahead, pause me, try this example. Okay, looking at this function, x minus 8 factors cancel. We still have 1 in the numerator. That's going to be a whole at 8. And then we have an x plus 3 that cancels. That's going to be a whole at -3. And then I have this x plus 1 squared in the denominator. That's going to give you a -1. If you're curious at all about the powers in the denominator, or this idea of multiplicity with discontinuities, do they mean anything structurally or graphically will they appear? And they will. This is what we call an even asymptote. It's a degree of 2 for this asymptote, and so the behavior of the function will approach the same way at that asymptote, either in the positive or in the negative direction. Odd ones will always go opposite directions at that asymptote. Cool little neat fact there, okay? All right, here is a practice problem. Please go ahead, pause me. I want you to try this example. Okay, here they want a vertical asymptote at 6, which means I'm looking for my factor is going to be the opposite, x minus 6. And this vertical asymptote, this factor is in the denominator only. So note, it's not going to be a or d. I threw those out because that's x plus 6. And then looking at the x minus 6 factor for b, it's shared in the numerator denominator. That is a whole. So our answer here is C. Did you get it? Hopefully you did. Hopefully you did. Okay, last practice example here. Go ahead, pause me, try this one. Okay, we got College Board doing College Board things on this one. They give you a function f, they give you a function g, and then they give you a third function p, and they say p is g over f. So it's up to you to go ahead and kind of decode this and substitute this function in. And when you do, this is the expression you get, x plus 2 over 3x minus 2 divided by x plus 2 squared. So we have an x plus 2 factor that reduces, and so our reduced function is 3x minus 2. Don't need the parenthesis there, but sure, why not? Okay, over x plus 2. Okay, well, where is that x plus 2 bigger? Where is it bigger? In the denominator. That's going to be a vertical asymptote. So our answer is vertical asymptote at -2. And there were no holes. No holes. Remember, it can only be 1. It can only be 1. That 3x minus 2 doesn't do anything. Okay? All right. Hopefully, especially in this practice problem here, it highlighted this idea. How do you find holes in asymptotes? Holes, shared factor in the numerator and the denominator where the degree is the same, most common, or sometimes it can be bigger in the numerator. Asymptotes, these are factors in the denominator. When set equal to 0, they create a discontinuity in the denominator, or it could be shared numerator and denominator if the degree is bigger in the denominator. That's going to be a vertical asymptote. Give a thumbs up in this video if you learned something. I'll catch you in the next lesson.